Chapter 1 A Mystery. A few years ago, I was giving a talk at Cornell University. One of my PowerPoint slides read, "Is God a mathematician?" As soon as that slide appeared, I had a student in the front row gasp, "Oh God, I hope not." My rhetorical question was neither a philosophical attempt to define God from audience, nor should seem to, imp- to, intimidate, to intimidate the math publics. Rather, I was simply presenting a mystery with which some of the most original minds have struggled for centuries: the apparent omnipresence and omnipotent powers of mathematics. These are the types of characteristics one normally associates only with a deity. As the British physicist James Jeans, 1877 until 1946, once put it, the universe appears to have been designed by a pure mathematician. Mathematics appears to be almost too effective in describing and explaining not only the cosmos at large, but even some of the most chaotic of human enterprises. Where the physicists are attempting to formulate theories of the universe, stock market analysis are scratching their heads to the to predict the market crash. Neurobiologists are constructing models of brain function, or military intelligence statisticians are trying to optimize resource allocation. They are all using mathematics. Furthermore, even though they may be applying formalisms developed in different branches in mathematics, they are still referring to the same global, coherent mathematics. What is it that gives mathematics such incredible powers? Ornstein once wondered, how is it possible that mathematics, as a product of human thought that is independent of experience, the emphasis as mind fights so excellently the objects of physical reality? This sense of utter bewilderment is not new. Some of the philosophers in ancient Greece, Pythagoras and Plato in particular, were already in awe of the apparent ability of mathematics to shape and guide the universe, persisting it as it seemed above the powers of human to alter, dare of influence it. The English political philosopher Thomas Hobbes, 1588 until 1679, could not hide his admiration either. In Leviathan, Hobbes' impressive position of what he regarded as the foundation of society government, he singled out geometry as the paradigm of rational arguments, seeing then that thought consisted in the right ordering of names in our affirmations. A man that seeks precise truth had need to remember what every name he uses stands for, and to place it accordingly, or else he will find himself entangled in words as a bird in lime twigs. The more he struggles, the more believed. And therefore in geometry, which is the only science that it had pleased God hitherto to bestow on mankind, men begin asserting the significations of the words with setting of significations, the call definitions, and placed them in the beginning of the reckoning. Millennia of impressive mathematical research and erudite philosophical speculation have done relatively little to shed light on the enigma of the power of mathematics. If anything, the mystery has, in some sense, even deepened. Renowned Oxford mathematical physicist Roger Penrose, for instance, now perceives not just a single but triple mystery. Penrose identifies three different worlds: the world of our conscious perceptions, the physical world, and the Platonic world of mathematical forms. The first world is the home of all of our mental images, how we perceive the faces of our children, how we enjoy our breathtaking sunset, and how we react the horrifying images of war. It is also the world that contains love, jealousy, and prejudices, as well as our perception of music, of the smells of food, and of fear. The second is the one we normally refer to as physical reality. Real flowers, aspirin tablets, weight clothes, and jet airplanes reside in this world, as do galaxies, planets, atoms, baboon hearts, and human brains. The Platonic world of mathematical forms, which to Penrose has an actuality comparable to that of the physical and the mental worlds, is the motherland of mathematics. This is where you will find the natural numbers 1, 2, 3, 4, all the shapes and theorems of Euclidean geometry, Newton's laws of motion, string theory, catastrophe theory, and mathematical models of stock market behavior. And now Penrose observes come the three mysteries. First, the world of physical reality seems to have lost the actual reside in the world of mathematical forms. This was the puzzle that left Einstein perplexed. Physical Nobel laureate Eugene Wigner, 1902 until 1995, was equally dumbfounded. The miracle of the appropriateness of the language of mathematics to the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research and that it will be extended for better or worse to our pleasure, even though perhaps also to our befuddlement, to wide branches of learning. Second, the perceiving minds themselves, the dwelling of our conscious perceptions, somehow manage to emerge from the physical world. How was mind literally born out of matter? Will we ever be able to formulate a theory of the workings of consciousness that would be as coherent and convincing as, say, a current theory of electromagnetism? Finally, the cycle is mysteriously closed. Those perceiving minds are miraculously able to gain access to the mathematical world by discovering or articulating a history of abstract mathematical forms and concepts. Penrose does not offer an explanation for any of the three mysteries. Rather, he laconically concludes, no doubt there are not really three worlds but one, the true nature of which we do not even glimpse at present. This is a much more humble admission than the response of the schoolmaster in the play 40 Years On, written by the English author Alan Bennett to a somewhat similar question. Foster, I am still a bit hazy about the Trinity, sir. Schoolmaster, 1 in 3, perfect straightforward. Any doubts about that? See your math masters. See your maths master. The puzzle is even more entangled that I have just indicated. There are actually two sides to the success of mathematics in explaining the world around us, a success that we never doubt the unreasonable effectiveness of mathematics, one more astonishing than the other. First, there is an aspect one might call a thief. When physicists wander through nature's labyrinth, they, they light their way by mathematics. The tools they use and develop, the models they construct, and the explanations they conjure are all mathematical in nature. This, on the fact of this, is a miracle in itself. Newton observed a falling apple, the moon, and tides on the beaches. I am not even sure if he ever saw those, not mathematical equations. Yet he was somehow able to extract from all of these natural phenomena clear, concise, and unbelievably accurate mathematical laws of nature. Similarly, when the Scottish physicist James Clerk Maxwell, 1831 until 79, extended to the framework of classical physics to include all the electric and magnetic phenomena that were known in 1860s, he did so by means of just four mathematical equations. Think about this for a moment. The explanation of a collective of experimental results in mathematicism and like, which had previously taken volumes to describe, was reduced to four succinct equations. Einstein's general relativity is even more astounding. It is a perfect example of an extraordinarily precise, self-consistent mathematical theory of something as fundamental as the structure of space and time. But there is also a passive side to the mysterious effectiveness of mathematics, and it is so surprising that the active aspect pales by comparison. Concepts and relations explored by mathematicians only for pure reasons, with absolutely no application in mind, turn out decades or sometimes centuries later to be the unexpected solutions to the problems grounded in physical reality. How is that possible? Take, for instance, the somewhat amusing case of the eccentric British mathematician Godfrey Hardy, 1877 until 1947. Hardy was so proud of the fact that his work consisted of nothing but pure mathematics that he emphatically declared, "No discovery of mine has made or is likely to make directly or indirectly, for good or ill, the least difference to the amenity of the world." Guess what? He was wrong. One of his works was reincarnated as the Hardy-Weinberg law, named after Hardy and the German physician Wilhelm Weinberg, 1862 until 1937. A fundamental principle used by geneticists to study the evolution of populations. Put simply, the Hardy-Weinberg law states that if a large population is mating totally at random and migration, mutation, and selection do not occur, then the genetic constitution remains constant from one generation to the next. Even Hardy's seemingly abstract work on the number theory, the study of the properties of natural numbers, found unexpected applications. In 1933, the British mathematician Clifford Church used the theory of numbers to create a breakthrough in cryptography, the development of codes. Koch's discovery, Koch's discovery made another statement by Hardy obsolete. In his famous book, A Mathematician's Apology, published in 1940, Hardy pronounced, "No one has yet discovered any warlike purpose to be served by the theory of numbers." Clearly, Hardy was yet again in error. Codes have been absolutely essential for military communications. So even Hardy, one of the most vocal critics of applied mathematics, was dragged, probably kicking and screaming if he had been alive, into producing useful mathematical theories. But this is only the tip of the iceberg. Kepler and Newton discovered that the planets in our solar system follow orbits in the shape of ellipses, the very curve studied by the Greek mathematician Menaeus, FLCA 350 BC, 2 millennia earlier. The new types of geometers outlined by Georg Friedrich Bernhard Riemann in 1826 until 66 in a classic lecture in 1856 turned out to be precisely the tools that Einstein needed to explain the cosmic fabric, a mathematical language called group theory developed by the young prodigy Evariste Galois, 1811 and 32, simply to determine the solvability of algebraic equations. Has today become the language used by the physicists, engineers, linguists, and even anthropologists to describe all the symmetries of the world. Moreover, the concept of mathematical symmetry patterns has, in some sense, turned the entire scientific process on its head. For centuries, the road to understanding the workings of the cosmos started with a collection of experimental or observational facts from which, by trial and error, scientists attempted to formulate general laws of nature. The aim was to begin with local observations and build a jigsaw puzzle piece by piece. With the recognition in the 20th century that well-defined mathematical designs underlie the structure of the subatomic world, modern physicists started to do precisely the opposite. They put the mathematical symmetry principles first, insisting that the law of nature and indeed the basic building blocks of matter should follow certain patterns, and they deduced the general laws from these requirements. How does Nato know to obey these abstract mathematical symmetries? In 1925, Miss Feigenbaum, then a young mathematical physicist at Los Alamos Natural Laboratory, was playing with his HP 65 pocket calculator. He was examining the behavioral simple equation. He noticed that a sequence of numbers that appeared in the calculations was getting closer and closer to a particular number, 5.669. To his amazement, when he examined other equations, the same curious number appeared again. Feigenbaum soon concluded that his discovery represented something universal, which somehow marked the transition from order to chaos, even though he had no explanation for it. Not surprisingly, physicists were very skeptical at first. At all, why should the same number characterize the behavior of what appeared to be rather different systems? After 6 months of professional reviewing, Feigenbaum's first paper on the topic was rejected. Not much later, however, experiments showed that when liquid helium is heated from below, it behaves precisely as predicted by Feigenbaum's universal solution. And this was not the only system found to act its way. Feigenbaum's astonishing numbers showed up in the transition from the ordinary flow of fluid to turbines, and even in the behavior of water dripping from a tap. The listing of such anticipations by mathematicians of the needs of various disciplines of later generations just goes on and on. One of the most fascinating examples of the mysterious and unexpected interplay between mathematics and the real physical world is provided by the story of knot theory, the mathematical study of knots. A mathematical knot resembles an ordinary knot in a string, with the strings and spliced together. There is mathematical is a closed curve with no loose ends. Only the main impetus from the development of mathematical knot theory came from an incorrect model from the atom that was developed in the 19th century. Once that model was abandoned only 2 decades after its conception, knot theory continued to evolve as a relatively obscure branch of pure mathematics. Amazingly, this abstract endeavor suddenly found extensive modern applications in topics ranging from the molecular structure of DNA to string theory. The attempt to unify the subatomic world with gravity. I shall return to this remarkable table in chapter 8 because its recorded history is perhaps the best demonstration of how branches of mathematics can emerge when attempts to explain physical reality, then how they wandered into the abstract realms of mathematics, only to eventually return unexpectedly to their ancestral origins, discovered or invented. Even the brief description I have presented so far already provides overwhelming evidence of a universe that is either governed by mathematics or, at the very least, susceptible to analysis through mathematics. As this book will show much, and perhaps all, the human enterprise also seems to emerge from an underlying mathematical facility, even where least, even where least expected. Examine, for instance, an example from the world of finance, the Blake Source option pricing formula 1973. The Black Source model, from its originator Myron Source and Robert Carhart Milton Fisher Black, passed away before the prize was awarded. The Nobel Memorial Prize in Economics. The key question in the model enables the understanding of stock option pricing. Options are financial instruments that allow bidders to buy or sell stocks at a future point in time at agreed upon prices. Here, however, comes a surprising fact. At the heart of this model lies a phenomenon that had been studied by physicists for decades: Brownian motion, the step of agitation motion exhibited by tiny particles, such as pollen suspended in water or small particles in the air. That as if were not that as if that were not enough, the same equation was also appear to the motion of hundreds of thousands of stars in star clusters. isn't it? Isn't this? In the language of Alice in the World in Wonderland, curiouser and curiouser. After all, whatever the cause may be doing, based on violence are definitely worlds created by the human mind. Oh, there are common problems encountered by electronic board manufacturers and designers of computers. They use large drills to make tens of thousands of holes in the boards. In order to minimize the cost, the computer designers do not want their drills to behave as accidental tools. Rather, the problem is to find the shortest for among the holes that visits each hole position easily once. As it turns out, mathematicians have investigated this exact problem, known as the traveling salesman problem, since the 1920s. Basically, if a salesperson or a politician on the champion trail needs to travel in the most economical way to a given number of cities, and the cost of travel between each pair of cities is known, then the traveler must somehow figure out the cheapest way of visiting all the cities and returning to his or her starting point. The traveling salesman problem was solved for 49 cities in the United States in 1954. By 2004, it was solved for 24,626, 24,978 towns in Sweden. In other words, the electronic industry companies routing trucks for parcel pickups and even Japanese manufacturers of pinball-like pachinko machines, which have to hammer thousands of nails, have to rely on mathematics for something as simple as drilling, scaling, or the physical design of computers. Mathematics has even penetrated into areas not traditionally associated with exact sciences. For instance, there is a journal Mathematical Sociology which in 2006 was in its 30th volume that is oriented toward a mathematical understanding of complex social structures, organizations, and informal groups. The journal articles address topics ranging from mathematical model, from predicting public opinion to what predicting interaction in social groups. Going in the other direction from mathematics into the humanities, the field of computational linguistics, which originally involved only computer scientists, has now become an interdisciplinary research effort that brings together linguists, cognitive psychologists, logicians, and artificial intelligence experts to study an intricacies of languages that have evolved naturally. Is this some mischievous trick played on us, such that all the human struggles to grasp and comprehend ultimately lead to uncovering the more subtle fields of mathematics upon which the universe and we, its complex creatures, were all created? Is mathematics, and as educators like to say, the hidden textbook, the one the professor teaches from, while giving his or her students a much lesser version so that he or she will seem all the wiser? Or to use the biblical metaphor, is mathematics in some sense the ultimate fruit of the tree of knowledge? As I noted briefly at the beginning of this chapter, the unreasonable effectiveness of mathematics creates many intriguing puzzles. Does mathematics have an existence that is entirely independent of the human mind? In other words, are we merely discovering mathematical verities just as astronomers discover previously unknown galaxies? Or is mathematics nothing but a human invention? If mathematics indeed exists in some abstract fairyland, what is the relation between this mythical world and physical reality? How does the human brain, which is known in limitations, gain access to such an immutable world outside of space and time? On the other hand, if mathematics is merely a human invention and it has no existence outside our minds, how can we explain the fact that the invention of so many mathematical tools miraculously anticipated questions about the cosmos and human life, not been posed until many centuries later. These are not easy questions. As I will show abundantly in this book, even modern-day mathematicians, cognitive scientists, and philosophers do not agree on their answers. In 1989, the French mathematician Alain Kohn, winner of two of the most prestigious prizes in mathematics, the Fields Medal 1982 and the Crawford Prize 2001, expressed his views very clearly. Take prime numbers, thus divisible only by 1 in themselves, examples which, as far as I am concerned, constitute a more stable reality than the material reality that surrounds us. The working mathematician can be likened to an explorer who sets out to discover the world. One discovers basic facts from experience. In doing simple calculations, for example, one realizes that the series of prime numbers seems to go on without end. The mathematician's job then is to demonstrate that there exists an infinity of prime numbers. This is, of course, a result due to Euclid. One of the most interesting consequences of this proof is that if someone claims one day to have found the greatest prime number, it will be easy to show that he is wrong. The same is true for any proof. We run therefore against a reality every bit as incontestable as physical reality.
Martin Gardner, the famous author of numerous texts in recreational mathematics, also takes the side of mathematics as a discovery. To him, there is no question that numbers and mathematics have their own existence, whether humans know about them or not. He once wittily remarked, if two dinosaurs join two other dinosaurs in a clearing, there will be there will be four there, even though no humans were around to observe it, and the beasts were too stupid to know it. Ascanius emphasizes supporters of the mathematics as a discovery perspective, which, as we shall see, conforms with the Platonic view, point out that once a particular mathematical concept has been grasped, say the natural numbers 1, 2, 3, 4, then we are up against undeniable facts such as 3 square, 4 square, 5 square, irrespective of what we think about these relations. This gives at least the impression that we are in contact with an existing reality. Others disagree. While reviewing a book in which Cons presented his ideas, the British mathematician Sir Michael Atiyah, who won the Fields Medal in 1966 and the Abel Prize in 2004, remarked, any mathematician must sympathize with Cons. We all feel that the integers or cycles really exist in some abstract sense, and the Platonic view, which will be described in detail in chapter 2, is termed deductive. But we can really defend it. Had the universe been one-dimensional or even discrete, it is difficult to see how geometry could have evolved. It might seem that it might seem that with the integers we are on firmer ground and that counting is really a primordial notion. But let us imagine that intelligence has resided not in mankind but in some vast solitary insulated jellyfish buried deep in the depths of the Pacific Ocean. It will have no experience of individual objects, only with the surrounding water. Motion, temperature, and pressure will provide this basic sensory data. In such a pure continuum, the discrete would not arise and there would be nothing to count. Atiyah therefore believes that man has created the emphasis is mind, mathematic, by idealizing and abstracting elements of the physical world. Linguist, linguist George Lakoff and psychologist Raphael Nunes agree. In their book Where Mathematics Come From, they conclude mathematics is a natural part of being human. It arises from our bodies, our brains, and our everyday experiences in the world. The viewpoint of Atiyah, Lakoff, and Nunes raises another interesting question. If mathematics is entirely a human invention, is it truly universal? In other words, if extraterrestrial intelligent civilizations exist, would they invent the same mathematics Carl Sagan 1936, 1934 until 96 used to think that the answer to the last question was in the affirmative. In his book Cosmos, when discussed what type of signal an intelligent civilization would transmit into space, he said it is extremely unlikely that any natural physical process could transmit radio messages containing prime numbers only. If we receive such a message, we would deduce a civilization out there that was at least found of prime numbers. How can certainly how but how certain is that? In his recent book, A New Kind of Science, mathematical physicist Stephen Wolfram argued that what we call our mathematics may represent just one possibility out of a rich variety of flavors of mathematics. For instance, instead of using rules based on mathematical equations to describe nature, we could we could have different types of rules embodied in simple computer programs. Furthermore, some cosmologists have recently discussed even the possibility that our universe is but one member of a multiverse, a huge ensemble of universes. If such a multiverse indeed exists, would we really expect the other multiverses to have the same mathematics? Molecular biologists and cognitive scientists bring to the table yet another perspective based on studies of the faculties of the brain. To some of these researchers, mathematics is not very different from language. In other words, in this cognitive scenario, after eons the, during which humans started two hands, two eyes, and two breasts, an abstract definition of the two number has emerged, much in the same way that the word bird has come to represent any two-winged animals that can fly. In the word of the French neuroscientist Jean-Pierre Saint, for me, the axiomatic method used, for instance, in Euclidean geometry is the expression of cerebral faculties connected with the use of the human brain. For what characterizes language is precisely its generative character. But if mathematics is just another language, how can we explain that the fact while children study languages easily, many of them find it so hard to study mathematics? The Scottish child prodigy Marjorie Fleming, 1803 until 11, charmingly described the type of difficulty students encounter with mathematics. Fleming, who never lived to see her ninth birthday, left journals that comprise more than 9,000 words of prose and 500 lines of verse. In one place she complains, I am now going to tell you that the horrible and wedge plaque that my multiplication table gives me. You can conceive it. The most devilish thing is egg times egg and 7 times 7. It is what nature itself can endure. A few of the elements in the intricate questions I have presented can be recast into a different form. Is there any difference in basic kind between mathematics and other expressions of the human mind such as the visual arts and music? If there isn't, why does mathematics exhibit an imposing coherence and self-consistency that does not appear to exist in any other human creation? Euclid's geometry, for instance, remains as correct today when it applies as it was in 300 BC to represent truths that are forced upon us. By contrast, we are neither compelled today to listen to the same music the ancient Greeks listened to note whether to Aristotle's naive model of the cosmos.
Very few scientific subjects today still make use of ideas that can be 3,000 years old. On the other hand, the latest research in mathematics may refer to theorems that were published last year or last week, but may also use the formula for the surface area of a sphere proved by Archimedes around 250 BC. The 19th century knot model of the atom survived for barely 2 decades before new discoveries proved elements of the theory to be in error. This is how science progresses. Newton, gave credit or not, see chapter 4, for his great vision to those giants upon whose shoulders he stood. He might also have apologized to those giants whose work he had made obsolete. This is not the pattern in mathematics. Even though the formalism needed to prove certain results might have changed, the mathematical results themselves do not change. In fact, as mathematician and author Ian Stewart once put it, there is a word in mathematics for previous results that are later changed, that they are simply called mistakes, and such mistakes are judged to be mistakes not because of new findings as in the other sciences, but because of a more careful and rigorous reference to the same old mathematical truths. Does this indeed make mathematics God's native tongue? If you think that understanding whether mathematics was invented or discovered is not the important, consider how loaded the difference between invented and discovered becomes in the question was God invented or discovered, or even more provocatively, did God create humans in his own image, or did humans invent God in their own image? I will attempt I will attempt to tackle many of these intriguing questions and quite a few additional ones and their tantalizing answers in this book. In the process, I shall review insights gained from the works of some of the greatest mathematicians, physicists, philosophers, cognitive scientists, and linguists of past and present centuries. I shall also seek the opinions, caveats, and reservations of many modern thinkers. We start this exciting journey with the groundbreaking perspective of some of the very early philosophers.